And today I will give you a talk about QSAR modeling. So let's begin. What we will cover today is, first of all, what is QSAR modeling? How did it begin? Then we will talk about how it is applied now. We talk about the methods which we use to create these QSAR models. Then we will discuss validation of models and their performance. We will also touch important concept of applicability domain and conclude our talk. So let's begin. As long ago as in the beginning of 20th century, doctors who performed surgeries under narcosis, under anesthesia, they started to notice that actually the power of anesthetic agents, the depth of narcosis is related somehow to the lipophilicity, or simply speaking, to the solubility of narcotic agents in the lipids, in oils. So for instance, chloroformium was one of the first narcotic compounds, and it gave rise to the lipoid theory of narcosis. And the observations continued to be collected, and in the middle of the century, two famous scientists, Hansch and Fujita, came up with the idea of a so-called quantitative structure relationship, structure-activity relationship. So they claimed that the activity, no matter what activity, like let's say biological activity of compounds, is related and actually can be quantitatively related as some formula, some equation to chemical structures of these compounds. So this is an example of chemical series of related compounds. And this is a simple QSAR equation. So the activity in logarithmic units is can be described as linear dependency of the nature of substituent in the aromatic ring, which here is denoted as P, and the nature of substituent in this position, which is sigma here. But after that, it continued, the studies continued to be performed. And in 70s, 90s, scientists developed more solid grounds, mathematical grounds, mathematical methods for this modeling. They developed descriptors, which actually, these are vectors or some set of numbers which can relate your structure, which can encode your structure, molecular structure, no matter which structure you take. So it's very universal representation, and you can easily encode it using zeros and ones or any real numbers. So just mathematical encoding. And I hope you remember what you've been told in the lecture of Wim de Haan about descriptors. So this is just a way to describe the structure. Later on, they also developed methods which are able to deal with three-dimensional structures, not just two-dimensional structures. So nowadays, these models are applied in drug design. And this is a typical pipeline of drug design development. And there are stages related to finding and validating targets, which you will hit. And there are stages related to small molecule, to the drug itself, or future drug itself. And in these stages, chemoinformatics, namely QSAR modeling, can be applied to first of all discover and then to develop these compounds into drugs. So this is again a virtual screening pipeline. How do you do virtual screening? So you can use molecular docking, molecular dynamics, but also you can use QSAR here to filter, to narrow down the initial number of compounds. So you can use a so-called filter or model, which will model of biological activity, model of some pharmacokinetic properties, ADME properties, solubility, or some physicochemical properties. And it's it looks like this. So you have your molecule of interest during virtual screening. So you want to know whether it is active or inactive. So you don't, without doing experiment, you can just take your model, which we will discuss how we create this model. Then you input your structure and you output, the model outputs the activity. So how exactly we do it? How exactly we create these models? First of all, for good modeling, we need a lot of data. The more the better. This data comes from experiments. So we can download some databases which you have, in which you have molecules and their corresponding activity. Or you can use your own data if you work in some research organization. And then you apply machine learning methods, also known as artificial intelligence. But strictly speaking, artificial intelligence is broader term, and machine learning is like a sub-part of it, which we will discuss today, exactly this. And then you can build mathematical model that activity is a function of structure, but more correctly to say structure a function of descriptors, because we describe our structures by descriptors. So we have our structures, we describe them or encode them by descriptors. Typically, it's called fingerprint. And then we create a model, which is this function of all these fingerprints, all these numbers, or they called bits in fingerprints. So these models are multidimensional. Here I show 2 dimensions, like bit 1, bit 2, but essentially in real world, you have many dimensions, and this function becomes very complex. And that's why we need to apply modern, complex machine learning methods, which we will exactly discuss today. So models can be of the most basic partition of models is 2 types: regression and classification, and also clusterization. So classification case is that when you have imagine you have your molecules, and some of them are good drug candidates. Let's say that they have favorable values of lipophilicity and favorable values for molecular weight, and they are here in green. So these are like, let's say, your good molecules or active molecules. And you have some molecules which are not favorable, and your task is to create a model which will classify, which will separate good from bad. So this is your setting. You could, if I visually, graphically show it, it can look something like this. So, and if I want to write down a formula, this or equation of this model, it will look something like this. So log P is greater than some value, no matter what, for instance, and molecular weight is greater than 500. And this is called classification problem, when you need to classify your data. Clusterization is similar to classification, except that you don't know which is good and which is bad, but you need just to find some grouping. You have to find some clusters of your data. That's why it's called clusterization. On the other hand, the other part is the other case of modeling is called regression. And this is, again, initially in the beginning, you have your molecules and you have some activity, let's say some binding to protein, and you want to find a model which will relate these structures to their activities quantitatively. So some molecules are low active, some molecules have higher activity, some molecules have even higher. And what you need to do is to create some function which describes all this behavior. So this is basic principle. How do we build these models? How exactly we create them? To create these models, we need to perform so-called optimization. So in classification case and in regression case, you can create your equation or model something like this. You can do something like this. So in classification, you can say that on this part of this border, good molecules are, and on this part, bad molecules are. Or for regression, you can say that, okay, my dependency between X and Y, in this case, X is your molecules and Y is your activity, but generally it can be anything. You can use these models even beyond chemistry, of course. So you can say that this is my dependency. This is a straight line linear dependency. So how do you find which is better? The way you find it is minimizing or maximizing so-called objective function. This is a technical term, but objective function is easy thing, is easy idea. For classification, this function can be just accuracy. So how many correctly classified molecules you have divided by overall number of molecules. So let's say in this case, you have 2 molecules which end up on the wrong side of this border line, right? So you have like 2 incorrectly classified. So correctly is 1, 2, 3, 4, 5, 6 divided by number of overall. So this is how you, and you need to maximize this accuracy. This is how you build your model. In regression case, an objective function can be a sum of squared errors. So this is very simple. You just take your observed values and your values which lie on your line, and you take the differences between them and square them and take sum of them. And in this case, you need to find the line which gives you the minimum error. So you need to minimize it. And also one note before we are finally ready to understand all the methods is that models can be linear and non-linear. Linear is, it is very simple. If it's classification, they look like a line or described with a linear equation. In regression case, they look like a line or like a plane if it's in 2 dimensions, or like a hyperplane when it is more than 2 dimensions. But in our modeling of biological activities, we almost always have non-linear cases because our body is complex, and how the compound behaves, how and why it binds to proteins or does whatever it does in body, it's always complex. So these models will be non-linear, something like this, maybe a model which separates your good or actives from inactives, or in regression cases, something like this. Again, it's not a straight line. So now we are ready to get to methods, how we build our models. Nowadays, we use machine learning, and the most important algorithms are these: random forest, gradient boosting. These are so-called ensemble-based or tree-based algorithms, neural networks and deep learning, and support vector machines. These are the most popular and common methods. So let's start with this random forest. As it is forest, it consists of many trees. So let's first discuss a tree. You have some molecules. Let's discuss classification case. So you have some active molecules, you have some inactive, and you need to create a model which will separate them. You describe molecules by some descriptors. Let's take 2 simple, understandable descriptors, lipophilicity and molecular weight. This is just for example. In real case, probably you will use some fingerprints, but for understanding and simplicity. So here are our molecules and together with their descriptor values. So what we do, we ask a question. We try to separate goods from bads using some questions, some decisions. So is molecular weight greater than, let's say, 75? If yes, then we say we put molecule on this part. If no, then on this part. And we could already separate some good molecules from bad, but not all. We continue to ask questions, and if we ask if logarithm p is greater than 0, then molecules are active, otherwise inactive. And now we are ready. The tree is ready. So if you want to write it down as kind of formula or equation, if you will, you can just write it down in this way. So the forest, it consists of trees, and you have your data set of molecules. Then you take some sample, some part of it, not all, and you build a decision tree just like we discussed now. And then you do another sample, build another tree, another sample, another tree, and so on. You build some number of trees, certain number. We discuss how many we need. And then what you do, you combine your predictions using majority vote. And majority vote is this. It looks like this. So for single molecule, you can ask your trees. And if 5 trees, for instance, majority of trees says that yes, it is active, and the 2 trees say no, it's not, then the majority vote is yes, it's active. And what it means, says it's active, it means that this molecule ends up in the leaf, which corresponds the last nodes in the tree, they are called leaves. So if molecule ends up in the green leaf, it means that this tree says it's active. Otherwise, it says it's inactive. Also, these trees can be built for regression tasks. So you have some molecules described by some descriptor X, no matter which for now, some descriptor, and you have some activities. These are your activities. So again, you can ask questions. So if X greater than 4, then you correspondingly draw a line like greater than some value, let's say 4 or less. And you model this, you assign the activity to all the molecules which are in the left-hand part and in the right-hand part as the mean activity of all of them. And then you can, actually you choose this Fx, this value, such that minimizes the error. Error is the difference between your data points, your real activities, and this line. But you see now at this point that the errors are quite high. So the difference between your actual activities and your mean activities is high. So you continue asking questions and splitting again and again. And then you stop when the loss is small enough. Loss is error. So it's just another word for error. When it's small enough, you stop. And you see that the deeper you go, the smaller errors you get. And the random forest in regression case looks just like it looked in classification. So you just take some samples, which are called bootstrap samples. We don't have time to discuss what is bootstrap, but I encourage you to read. It's easy to find on internet. And so you build several trees and you combine them into combined prediction. By now, you may ask a question, why do you need combine? Why don't you build just single tree and that's it? And the answer to that is that all the models, be it random forest, be it neural networks, which we will discuss later today, all the models are all stay in danger of overfitting. And actually building many trees is the way how to deal with it. So first, what is overfitting? Imagine you have some regression model. So this model goes, it's not linear model, it's not straight line, it goes nicely through your data. So you can see that the error, the difference between predicted values by your model and the true values is little. So you can say, okay, my model is good. But imagine you use your model in virtual screening. And this symbolizes the molecule which appears in virtual screening. And you can see that you don't know the activity because it's screening. So you have some molecules and you don't know if they are active or not. Your task is to define it out. And you use your good model. And then you see that the difference between predicted and true value, let's say we know the true value. Let's say we test this molecule later on in the laboratory. And you see that the difference is quite high. So this model, but imagine you have another model which goes through the same data, but it's just a straight line. And for the same molecule, you will have smaller error. And such model, which is better performs on real data, is called strong predictor. It's better predicts and it learns true patterns. So you know, of course, that in the experiment, you have some noise. And actually, the model which is able to ignore the noise is better than the model which nicely goes through noise. So these models which learns the noise, they are called overfitted models. There is another, the other opposite problem, which is called underfitting, when your model is very complex and you, it's very simple, and you need something more complex, but we will not talk too much about it, just for your information. So overfitting and underfitting are problems which you should keep in mind when you build your models. So next algorithm which we want to talk about is called neural networks, and also deep learning as a part of it. So as the name suggests, it has something to do with our brains, with our neural networks in our brains. Our brain, human brain or animal brain, is the source of inspiration for all these methods. So in your brain, you have neural cells called neurons. And these neurons are connected, and the connection is called synapse, right? And the signal, which goes from one cell to the other, which is called action potential, it goes through this synapse, and the strength of this signal can vary. So scientists were inspired by this. It was long ago, in the middle of 20th century, but these models became very powerful and common and popular only recently, like 30 years ago, 20 years ago. It was real new age of this methodology. So the simple model which can represent this situation can look like this. You have some nodes, you have some weight between. Weight is the value by which you multiply the signal. So the signal goes from node to node, and it's multiplied by value. And also inside the neuron, there is so-called activation function. So the signal is a little bit transformed because if the signal is too low, then the neuron just doesn't generate any value. And it's same in biology and same in this mathematical model. So you combine these neurons into a network, and then what you do, the value which you have here, it is actually your molecule. So you have your descriptors for your molecule. For instance, again, just for simplicity, we will use logarithm p, molecular weight, and for instance, number of hydrogen bond donors. You pass this signal through the model and you get the output value. So it looks like this. You feed your data X, which is these descriptors, through the network, multiply in each connection between the new nodes, you multiply by weight, and then you change weights until the output, and you get your output, and until the output is close enough to your Y. Your Y is activity of your molecule. So it looks something like this. If you have your data, you need to create the model, which is function of these weights. W is big W, which represents not single weight, but all these weights. So you create a model which looks something like this, and which fits your data. So how do we create these models? How do we know which weights to choose? The method which you use, the method which all the neural networks use, is called gradient descent. So imagine yourself somewhere on the top of the mountain, and you can go downhill to the bottom in some strange way. You can go straight way, and this straight way is faster. So imagine that you, remember that we need to find some good weights in our network, which will give us the output of the model, the activity which the model predicts for molecules, close to our real activity. So we can use this method. These are our weights, and the L, or error or loss, this is what we want to make as small as possible. So the difference between real data and prediction by your model. So what you do, you just make steps in this space until you get to the very bottom, where, or not very bottom, but good low enough value, which gives you the low L. And in each step, you compute gradient of this L with respect to these W's. I will not show it here. It's a beautiful picture. Let's not spoil it with formulas. So the idea is like this. And this is how you train your models. There are many possible ways how to connect these neurons into networks. What we discussed before is called multi-layer perceptron, is when your signals flow only forward. But also you can have some network where your signal goes backwards. It's called recurrent networks. And the good thing, the usefulness of these networks is that they are used for tasks related to text, to language processing. For instance, machine translation, Google translation, although now in Google they use more powerful models called transformers, but these recurrent models are very well for tasks related to text. And it is useful in our cases of QSAR modeling because you can use smile strings, which are text, right, as input to these models, and you don't need to create descriptors, you can just use smile strings. And also another important architecture, which I really want to cover because it's important in chemistry, it's called graph neural networks. And if you have a molecule, we talked so far that we create some descriptors and then we perform modeling. But I can use graph network. And in this case, I don't need to create descriptors. So let's say that I claim that I don't want to create descriptors because I don't know which descriptors would be good for my case, for my task. So instead, I can use so-called graph convolutional network. And I can see that my molecule is a graph, right? And it can be a neural network by itself. So you have your nodes as atoms, and bonds, chemical bonds, are your connections. So you have weights which go this time, in this case, they go both directions to, like, in every connection, they go bidirectionally. And then you can just train a model which finds the best W, which will give you the best, good model which predicts your activities quite well. So this was all about algorithms for today. And let's talk about models validation. Let's say that we already have our model built. And we talked a few slides ago that these models can have some problems like overfitting. So what we need always, as with every computational methodology, like be it docking, molecular dynamics, pharmacophore modeling, whatever, it's always good to have some test, some validation before you apply. So there are two basic methods of how to validate your models. First is called external testing. So you split your data on some 80-20% or 19-10. Then you take the larger part and build a model, and the smaller part you use as a test. And you see how good your model is with this test. But the problem is here, as we said in the beginning, it's good to have a lot of data for good models. But here we sacrifice 20% just for testing. So we sacrifice some data. Another good way to validate models, which is standard way nowadays, called k-fold cross-validation. So you split your data into 10 or 20 or how much you want, equal parts. It's K. And then you build a model using all the 9 parts and test using this 10th part. Then you build model using another part and test using some other part. And you repeat it 10 times and you have 10 models. And then you just average the results of 10 models to get final model. So the good thing about it is that from the point of view of information, you use all the information, all the molecules, because finally you aggregate them together. And at the same time, you have your test, right? But also what is good about this cross-validation, that during cross-validation, you can choose what is called hyperparameters for your model. So parameters for your model are, for instance, for neural networks, are these weights, which we wanted to find the best. But there are also some parameters which you cannot find the best value of during training. You have to choose it beforehand, and these are called hyperparameters. You will talk about it during tutorials. So this cross-validation is also good for choosing hyperparameters. So how do we, what metrics do we use to evaluate our models? We need some quantity, some number. So for classification, the simplest and the most basic metrics come from what is called confusion metrics. These metrics are sensitivity, specificity, and accuracy. So when you have your model, you can see how well it performs, and you can compare your real data, your true activities, to predicted. So you have some molecules for which true activity is the same as predicted, so it's correctly predicted as positive. It's called true positives. You can have true negatives, likewise, those for which it was which are inactive, and the model says they are inactive. And you have incorrect predictions, errors, false positives and false negatives. And having this data, you can compute specificity, which reflects how well your model is on class 0, on negative class or inactive class. Sensitivity, which is how well your model performs on positive class, and accuracy, which is just overall how your model performs. But when your data is imbalanced, which means that the number of inactives and active is not the same. Some of, like, for instance, you have 1,000 of active molecules and 100 of inactives. This is called imbalanced data, and then it's better to use balanced accuracy instead of accuracy. Regarding regression, you have, so this is your regression model. This is your line. You have your predicted values, which are lie on this model, which are black, and observed, which are orange values. And this blue line is average, is mean of all the observed values. So these differences are called, in technical language, they are called residuals. So what you can do for regression is to calculate the determination coefficient, which is simply, in the numerator, you have these errors, these differences, and the smaller the better they are. And in the denominator, you have the these observed values divided by the mean value. So this reflects the range of your data. How large is the range of your activities? So it is called variance. So if you have small errors compared to this overall range, then you have low value here, and you have 1. So 1 minus this low value gives you something about 1. So 1 is good value of determination coefficient, which tells you that the error is low. And if the errors are high, then it will be close to 0, or sometimes even negative, depending on concrete way how you can define this formula slightly differently. So regarding the other metric is called root mean square error, and it is just a numerator of this formula, but you take the mean of it and take the square root of it. So this reflects how small or large your errors are on average. Also, I would like to talk about applicability domain of models. This is a very important concept generally in modeling, and in chemistry, in chemoinformatics, we really care about it, I would say, more than in other fields of machine learning. So imagine you have a model which gives you the relationship between boiling point of alkanes and their structure. And my question is, can you reliably predict the boiling point of acetic acid using this model? So short answer is no, because this model was built for alkanes, and now you use acetic acid. So this means that your data is different from what you used to create your model. And how would you define it? Formally, you can define this applicability domain as a box. So you have some descriptors of your molecules, and you just bound them into a box and say that only the molecules which are within this box can be reliably predicted using our model. or you can draw a circle. It's a matter of taste, basically, or some other considerations. So that's all I wanted to say. And also, I did not say some important things. So we didn't cover methods like support vector machine, gradient boosting. They are also very powerful. They are used a lot. I encourage you to read about them. There's plenty of materials, videos, everything online. It's now very easy to get it. Also, we didn't cover nice, important thing, which is so-called inverse QSAR. So we said that structure can be, the model can be created in a way that you build activity as a function of structure, but you can do vice versa. You can find structures which have good activity. So you can say, I want this and this activity, and you can, using these machine learning methods, you can generate structures. Also, as I said, we didn't cover hyperparameters, so you will have it on the tutorial. This is important when you build your models, because if you don't care about choice of hyperparameters, you can end up with very bad models. And also, we didn't cover model explainability. So models are very complex, and sometimes it's useful to use some methods to look inside and to analyze the decisions which models make. So our conclusion is that QSAR is mathematical methodology, which is used to produce models which relate structures to activities. It's really fast and easy compared to structure-based models. So you need only your molecules. You don't need to have protein structure. Yeah, it doesn't need structural information, but it always requires careful validation. So remember it. And for this, you have to use some validation techniques, and also to consider applicability domain. And the best results can be achieved in these models when you combine them with all the other methods which you can do. So thank you for attention. And I'm open to questions.
Questions?
If any.
So you talked about the optimization problem of the weights in the neural networks. So I guess it can end up in local minima. So
yes.
And also it's a matter of time. So is it somewhere useful to try to go to deeper minima using some Hessians or certain derivatives, or is it just it takes too much time and it doesn't bring enough of improvement?
Yeah. Okay. So the aim of learning is to get deeper minimum. It's for sure. And in which minimum you end up, you of course never know. But because in reality, you never know. You can never visualize the real surface manifold of this error function. But you assume that it, of course, has multiple local minima. So one way to try to get better minimum, deeper minimum, is to run models several times. So you do, in the beginning, you do some random initialization. And I mean that the weights, you just assign them some random value, and then you train the model, and then you assign another random value, and then also train. And now this is standard practice. I think that you just run several runs and see how well it performs. But I think there are some other ways to get deeper. There are also always ways. I'll have to think about it.
Do we have questions from online?
I don't know any questions.
The audience? Okay, so we have to wake up then. Thank you.
Yeah, thank you.
Save us 5 minutes.
Oh, even so.
Yes.
Okay.
We can start a little bit earlier.
Okay.
We will see how much time I have. Okay, I hope works. Okay, so let's start the second part of machine learning session. I hesitated which topic to present for you because in my group we work quite a lot on model interpretation to explain how models make a decision, which may help to researchers to understand and trust these models. But finally, I decided to show you recent developments, or we will see, is it really new or not new, these developments. But in my opinion, it's quite interesting approaches for modeling of properties of chemical compounds, which were forgotten for many years. And now we try to resurrect this kind of approaches. So I hope you will enjoy the story. So the story named multi-instance learning. What does it mean? We will see. When we perform machine learning, when we build machine learning models for chemical, to solve chemical tasks, we usually represent our structure at different levels. And the most popular one is a 2D. When we look on a molecule, on a molecule, generate some topological descriptors and find the correlation with our property. This is the most frequently used, commonly used, very fast approach, reliable one, but not all any other approaches. Possible to use less complex or more complex descriptors. And when you use descriptors, you definitely lose some information. So when you look on a molecule as a molecular graph, it's just a skeleton of a molecule. But in reality, molecules interacted through their surfaces. So it's important to know the shape, size of a molecule, and other 3D properties, because they interact in 3D space. And when we look on those skeletons, we not always can understand what is behind this one, because if you have a skeleton, one can have one idea, another one can have other idea how it should look like in reality. So that's why if we lose information, we may get worse models. And people started to think about this problem many years ago. This is a famous work of Kramer, where he started to use 3D modeling in QSR. The idea was very simple. So we took single 3D conformers of our compounds, active and inactive ones. We align them in 3D space according to the common scaffold. This is the most common option. Then put these molecules in 3D grid. And then we place a probe atom in every cell of this grid and calculate interaction energy with this probe atom. Probe atom can be hydrogen or carbon of sp3 hybridized carbon, but some other probes can be used as well. And when you calculate this interaction energy with your probe atom, you can create then large table of our descriptors, where each value of this cell will be equal to the interaction energy of a particular probe atom in this 3D grid. And then we can apply ordinary machine learning methods. Classical is a partial least square method to find a correlation. It's a very good, very straightforward approach. So it's very clear. It has another additional advantages that it can be interpretable because those weights which we obtain in this linear equation for different cells can inform us about the importance of a particular kind of physicochemical properties. For example, electrostatic interaction, hydrophobic interaction. It depends on which probe we use. And we don't need to somehow encode stereochemistry because this is quite a big problem for 2D representations because we cannot explicitly encode stereochemistry. So we should create some tricks to do this. But in 3D case, there is quite clear representation. But this approach had multiple disadvantages. Many of them were solved during the further research studies. So the first one, it can be dependence on the alignment, how you align your molecules, because classical approach works only if you have a common scaffold. But if you have a large set of molecules, which are now quite diverse, usually you cannot find the common scaffold to align them all together. But the biggest issue of this approach is that they depends heavily on the chosen conformer and how you choose this 3D conformer for each molecule. Of course, Kramer developed this approach and tested it on very rigid structures, on steroids. But for flexible molecules, this approach would be so easy to apply because you have to decide which conformer to choose for alignment and for modeling. That's not so easy because we don't know which one is a bioactive. Because if we will align not bioactive like conformations, our model probably will be not so good. So that's the reason why 3D QSAR not always result in a good output, finally, and it didn't become very popular. So in in traditional 2D QSAR, we have some molecular graph, some descriptors represented this molecular graph, and 2D model. In 3D, we have a 3D structure, some descriptors derived from this 3D structure, and again, build a model. But if we represent our molecule with multiple conformers, how we can deal with this stuff? And of course, people are very smart, and they were suggested approaches similar to CONFA. Also, many years ago, it was a work in Hopfinger, and they did similar things. So they enumerate possible conformers by conformer generators. Then they align all these conformers of the same molecules all together. Then align all other conformers of other molecules all together and combine them all. And again, place in a grid, and they calculate occupancy of each grid point for every molecule. So it's like an average occupancy across multiple conformers of every molecule. So not one conformer, but multiple conformers. And again, you can create the large matrix of your descriptors and find the correlation. So the important thing here is that they averaged those descriptors across conformers. I just pointed out, because we will use this information later. So this somehow partially solves this issue with the choosing of a proper conformer for modeling. And there are quite a lot of studies in 4D QSR. This is its name. But unfortunately, there were not so obvious advantages because it requires a lot of calculation, additional calculation, but the benefit was pretty low frequently. And this is one of those work published by Denifouche, where they tried to compare 2D, 3D, and 4D models. So they generated conformers based on molecular dynamics for their ligand. They built model for 2D descriptors, and they obtained value of R squared 0.7. Then they add 3D descriptors for one conformer, and they improved a little bit on just, it becomes 0.73. When they add some 4D descriptors calculated from MD simulations, they improved a little bit more, 0.75. But alone those descriptors from MD, they didn't work. So models were pretty bad. So this just demonstrates that alone this approach may not work properly. Yes, the first issue is alignment. It is still exists in these approaches based on the grid. But okay, you can take some alignment independent descriptors and use them to represent your 3D structures. For example, it can be the distance between the most distant atoms in your molecule, in your conformer. And this value can be used as a descriptor, for example, of a shape and so on. And again, when researchers calculate a single descriptor string for a molecule, they always average descriptors for individual conformers. Yeah, so here is other. So advantages are the same as for confa, for example. As I described, alignment issue can be solved with alignment independent descriptors, not using the grid point. All conformers are treated equally. Because when you calculate the average, you use just an ordinary mean value. Of course, you can weight somehow those conformers based, for example, for Boltzmann distribution, but it may not be reasonable as well because those distributions frequently calculated in a vacuum, but molecules interact in water medium, they can have different distribution values, and this complicates the calculation as well. However, almost at the same time, in parallel with Hopfinger and his 4D QSR, Dietrich suggested an approach which named multi-instance learning. And the idea behind was very clear. So we have our objects, molecules. Green circles are positive active molecules, red inactive molecules. Every object can be represented by conformers, for example. These are conformers, and those green circles are bioactive conformer, and red triangles are inactive conformers. And the idea behind is that active molecules should have at least one bioactive conformer, while inactive molecule should have all conformers inactive. And the task was to find a hyperplane. For example, if you talk about SVM, Mariia didn't stop on this topic, but it doesn't matter. So we tried to separate those actives and inactives molecules, not based by their single conformer, randomly chosen, but on multiple conformer. And we try to separate those active conformers of every active molecule from any other conformers of inactive molecule. So it's quite clear, quite smart. He implemented this with its own approach. We'll discuss it in details. And how is this can be implemented? This approach was originally suggested for solving chemical problem. And then for many years, it was abandoned because I will show you just few papers were published after that time. So this paper was published in 96. And we found just 6 papers maybe, which were published on this approach in chemoinformatics. But this approach became very popular in computer science for modeling of multiple issue properties and data sets for speech recognition, image recognition, and so on. And the community developed a lot of approaches which can be classified or grouped in three large sets. The first one is a simple naive approaches which called wrapper. And the idea behind is that we can translate multi-instance problem to single instance one, like it is done in 4D QSR. In first case, bag wrapper means that we have some instances, like in this case, conformations of our molecule. We calculate descriptors, and then we average those descriptors in one single descriptor string, and applying the single instance algorithm like random forest, linear regression, doesn't matter, to find the model and predicted value. And this is what is exactly done in 4D QSR. So in this term, 4D QSR is a subset of multi-instance solutions, I would say. Another approach, which is also pretty simple, is instance wrapper. So we again have a representation of every molecule by a multiple conformer, generate descriptors, but in this case, we attribute the property of a compound to every conformer and build a model using all this information together. So if we had 10 molecules in our training set and every molecule had 10 conformers, our final training matrix would have 100 rows. So it's just multiply number of objects which we model. And all these conformers treated as having equal activity. And after this modeling, we obtain predictions for every conformer, and then we average the predicted activity across multiple conformers and get the final value. So it's a little bit another approach. There were developed a lot of so-called conventional approaches. There are adapted approaches like SVM, KNN, random forest, decision trees. Multiple of these frequently used approaches were adapted to solve multi-instance problems. Quite a lot of approaches were suggested specifically to solve multi-instance problem, like this one. I decided to show you. It names diversity density. So the idea is that if we have those bags or objects with multiple instances, they have the same shape. Green one are active, red one are inactive. And the idea behind is to find a point in this feature space. Here is the descriptors. To find a point in this feature space where multiple instances of positive objects are close and all inactive instances are far from these areas. And when we predict a new one, we get again some set of instances, and we're looking for the distance between the instance and this density point. If it is close enough, we can predict this molecule as active, for example. So it's the way how to find some dense region in feature space populated with instances of positive class. But today we have very popular neural networks, and of course neural networks were adapted to solve these multi-instance problems as well. And quite common architectures are very similar to those wrappers. The only difference is that initial descriptors supplied for every instance were passed through dense layers to convert them to some internal embeddings. And those embeddings were already averaged or somehow other aggregated. We can use some other functions to aggregate those predictions, those descriptors, to get a final representation and find a correlation with our property. InstanceNet have the same ideas as instance wrapper. And again, these initial descriptors are passed through the neural network, and we get some predictions for every instance, for every conformer, which were then aggregated again in one single predicted value. So it's pretty similar to those naive approaches. And more sophisticated approaches exist also. One of them is attention network, because in all previous cases, we treated those instances as equal. Because if we calculate the average, we do not prioritize any of those instances. But not all of them are equal in reality, because only some of them are really contribute to your property, not all instances and not all conformations. And it was suggested to use attention network. So it's additional network which assign weights to your embeddings. And when you calculate the average or aggregate those embeddings, you use these weights, and this allows you also get a final prediction value. And as a side effect, using these weights, you can get information about the most important or relevant instances for your modeling property. That gives you opportunity to get additional information about, for example, bioactive conformants. And this is quite important feature for multi-instance learning models, because they allow you to identify key instances. Again, a lot of approaches were developed for model-specific and model-agnostic cases. For example, for model-specific, if we're talking about instance wrapper, we had predictions of every instance, and we can use these predictions directly. So, for example, instance with the highest predicted value, sorry. Instance with the highest predicted value can be decided as a key instance, for example. In model agnostic approaches, you can show to your model just one selected instance, predict value, and decide whether it's good or not. Or, for example, you can remove one instance from a set of instances, make a prediction, and calculate the difference, how much accuracy dropped of prediction. Because if you remove some relevant instance from the set, the accuracy should drop significantly. So there are multiple such approaches, and this is quite attractive. I will show you several examples, because we tried to benchmark all these approaches, which I discussed now, on large collection of Campbell compounds, on almost 200 data sets. And we used for their modeling 3D pharmacophore descriptors, which were developed also in our group several years ago. The idea behind, I will not discuss in very details. If you are interested, you can look at the paper and go to the GitHub repository to check. The idea was, for conformer, we can assign pharmacophore features like Thierry showed you yesterday, and then we can remove a molecule and consider these pharmacophore features as a complete graph. And we split this complete graph on subgraphs of size 4, so for quadruplets. And we encode these quadruplets in some way, I will not discuss it in detail, which composition, distances, and chirality of those quadruplets. And the set of all quadruplets represent somehow our conformer. So this was our descriptors. Then we calculate and enumerate up to 100 conformers for every molecule in our training set with very hard, with almost any restriction on energy. So it's just to get as much diverse this conformer set as possible. So we didn't make any pre-selection of conformers. So we generate all of them by RDKit. And then calculated 3D pharmacophore descriptors. in total, in the beginning, we had quite a lot of data sets, but from the final evaluation, we removed those data sets which didn't achieve high accuracy on all modeling approaches. So they may be not modelable at all, those data sets. For the remaining 130 data sets, we calculate the performance of different kind of approaches, and what we discovered that naive multi-instance wrapper performed best of all. So when I just remind you, when we model every instance as a single object and build single instance model like usual one. In this case, we use random forest. And all other approaches were pretty close to each other. So if we try to rank them, we will find that there are no statistical difference between BAGNet, attention net, instance net, or bag wrapper. So they all perform similar but worse than this instance wrapper. And at this point, probably this may somehow already explain why those 4D QSARs didn't become very popular, because they used as a backend actually those bag wrappers, and those bag wrappers do not perform best of all. So there are some other schemes how to aggregate those instances. So this could be an explanation. Then we try to compare this top performed approach, instance wrapper, with traditional 2D and 3D approaches. For 3D single instance approach, we took the most energetically favorable conformer and build a model. And what we see is that in average, the quality, the performance of models obtained by this multi-instance wrapper is better than 2D models. It was quite surprising for us because it's quite common idea that 2D models perform very well and it's very difficult to improve them. However, we could do this. And those back attention, which are quite advanced architecture for multi-instance learning, it performs similarly well as 2D in average. Here, single instance 3D QSAR models perform in average like a random selection. So they cannot well prioritize your molecule. So this is another evidence that single instance 3D QSAR isn't working well. So it can work for very homogenic series of compounds which can be analyzed together and not very flexible. We collected some statistics which models performed best of all in top one for every data set. And we found that this instance wrapper performed on top in more than half cases. Then on the second place was 2D models. On the third place was bag attention, and only in one case 3D single instance model behaves best of all. And what is interesting is the distribution of accuracy of models calculated with 2D descriptors and single instance approach and multi-instance wrapper. So here we see just data points and data sets which achieved at least 0.4 accuracy for at least one of these modeling approaches. And what is interesting, those two the plots are almost the same, just different representations, that some data points like these ones, they have very bad prediction in 2D cases, but they were improved in the case of 3D multi-instance approach. Of course, there are some opposite examples where 3D multi-instance didn't work, but 2D QSAR worked well. But in these cases, we see quite large improvement, those green lines. And the results of 3D multi-instance models were more consistent, I would say, across multiple data sets. Of course, they are not always best, but in some cases where 2D models do not allow you to obtain good predictions, it can be reasonable to use something more complex for modeling. Then we asked ourselves, what are the reasons why 3D models, multi-instance are better and 2D worse? We analyzed different physicochemical properties of those data sets which we used, and we found only one quite weak evidences, in my opinion, quite weak, that those data sets where 3D multi-instance models performed better, they had in average less number of rotatable bonds, which means that these molecules are more rigid. So maybe you may expect that your 3D multi-instance will work better for more rigid structures. At the same time, 3D multi-instance models performed better if you have higher diversity of your molecules. You have higher number of unique Murko-scaffolds. And this can be also quite expectable because for 2D QSR, it's more difficult to find patterns across very diverse scaffolds. And here is the issue, I think, in the descriptors which were used, because for 2D QSR, we used descriptors discussed by Wim, extended connectivity fingerprints, like circular fingerprints, which encode local environment of every atom. And in case of multi-instance models in 3D, we used not a local descriptors, but pharmacophore descriptors, which are quite abstract and they do not rely on particular structure. So maybe this also can be an explanation. And we performed some additional analysis of whether we can identify bioactive conformants. So these key features from our 3D multi-instance models using the attention network, like I discussed previously. So what we did, we had several test sets and we collected information from PDB where those test molecules were solved in a crystal structure of a protein. And we calculate RMSD between these binding pose from PDB and the poses discovered by our approach, by RD-kit generation, or by Autodoc Wiener. What these bars mean? So yellow or light orange one is the total number of PDB structures in a particular test set. So these compounds were not used for training. They were present only in the test set. Those compounds were also selected to make the most challenging thing, because we selected compounds, only those which have average RMSD to the bioactive pose greater than 2 angstrom. So it means that almost a half of your conformers for a molecule have quite bad correspondence to bioactive conformation. So this is an additional challenge. Then this dark orange bar indicate how many compounds have for how many compounds we can randomly choose proper conformer from our set of conformers. So this is our baseline. It means these are quite high values. So for example, out of 59, for 9 compounds, we can just random, if you choose random conformer, for 9 compounds, we can discover a proper conformer. It means that the RD-kit generator of conformers behaves really good, and it generates really reasonable conformers. Then those 2 bars, green one means if we choose the conformer with the lowest energy, how well it corresponds to the bioactive one. And you can see that they not always happen. So the lowest energy conformer calculated in vacuum doesn't always correspond to the biactive conformers. The blue one bar is the top one docking pose, which was retrieved by AutoDoc. Top one, no, top three. So yeah, we selected top three. I'm sorry, I forgot this feature, that we selected top three compounds randomly, top three energetically favorable one, the top three poses from AutoDoc, and we see that AutoDoc behaves not much better than the random choice. So that's also quite unusual. And what was even more surprising is that those light blue bars indicate how many cases we can identify proper conformer using our attention network. So in some cases, it behaves much better than the random one and much better than the AutoDoc. And it is quite surprising because we built a ligand-based model without any knowledge of a receptor structure, and we can retrieve biactive conformer. For me, it's something very great. So, but I don't say that we don't need receptor structure. So that's not true. But this is really attractive feature. So we can, not in all cases, yes, in some cases we behave like any other approaches, but we can observe really improvement. Of course, unfortunately, we cannot make some more strict conclusions because the amount of data is limited, and this is just for set of examples, but we try to make this as much challenging as possible. So that's why we selected only those compounds which had quite large RMSD generated by RDQ. How much time do we have? I just need to check. Okay. Some other examples where we applied these 3D multi-instance approaches. We applied them for modeling of enantiomer selectivity of catalysts. So we have some catalyst which catalyze particular reaction with R and S isomers. Here is a distribution of enantiomeric excess values. And what we did, we represent, we generate for catalysts different conformations and represent them with descriptors similar to those pharmacophore descriptors. The idea was pretty similar. We didn't use pharmacophore features explicitly. We used just particular atoms, but we again encode conformers as quadruplets in 3D space. And reactant we represented by conventional topological descriptors. In this case, it was Izida descriptors. And then we combine those strings, so our reactant descriptor, our descriptor of catalyst, and we create a bag of instances. And in this bag, this part from the reactant was the same, and this part was different for different conformation of a catalyst. And then we built a multi-instance model and predicted an enantiomeric excess of these compounds. To properly validate these models, we built them in different scenarios because we had a complete matrix of catalysts and reactants, and we used for training just a small portion of this data. And we tried to simulate situations when we need, for example, to predict new reactions. So we used the same catalyst and tried to predict how they will behave on new reactants, which were unseen to the model. These are reaction out validation procedure. Or we simulate the scenario when we use the same reactant, but new catalyst. would our model trained on this set of data points will be able to predict new catalysts, how well it is possible. And the most strict scenario when we try to predict reactions occurring with new reactants and new catalysts. And what we get finally is that using 2D models, 3D single instance model, 3D multiple model, and model from the literature, which used as a reference one. So for reaction out case, we can quite reliably predict how an enantiomeric excess for new reactants for all already known catalysts with different approaches. So there is no reason to use more complex approaches, and it is expectable. For catalyst out case, it is already becomes obvious that using simple 2D model or just 3D model is not that profitable, because they are not so well in predicting new catalysts, because new catalyst brings new 3D steric requirement, which cannot be captured by simple 2D representation of those catalysts. And single instance model in 3D also behaves quite bad. And for the most complex case, we also see that multi-instance model behaves best across these two simpler approaches, and it behaves on par with the reference model, which was built on also quite on the similar idea as a 4D QSR. They calculated average occupancy, they aligned all catalysts all together, and that's why their model are limited only to this particular series of catalysts, which have the same scaffold. Our approach, since we used alignment independent descriptors, can be applied to wider range of catalysts. We didn't test this because we don't have experimental data to validate this idea, but from general point of view, this consideration is reasonable. Another example is how far those models can extrapolate, because it is more interesting to using available data to predict catalysts with a higher enantiomer selectivity. And we simulate this in such a way, so we split the whole set on a training one, where we selected cases where enantiomeric excess was below 80%, and all other examples went to the test set. We build again 2D models, the 3D single instance and 3D multi-instance models, and calculated accuracy on the test set. And what we see is that, unfortunately, you probably do not see the different in color. So gray color is the test compounds. So 2D models cannot extrapolate too far. So they predict something quite high values, but it cannot predict some exact values, that it will be 100% or 90% or 80%. 3D single instance, it starts to extrapolate a little bit, but multi-instance extrapolate a little bit better. So even training on limited data, you can get information about something better, and this can help you in real use cases when you want to discover something better, some new catalyst with better selectivity. And at the end, I just collected some set of examples from literature. There are just few of them from cheminformatics. There are a lot of papers in bioinformatics field or using multiple instance learning. So not only conformers can be used as instances. For example, atoms can be also considered as instances. And actually, currently widely used graph convolution models, Mariia didn't talk about this, but they're quite widely used. They can be considered as a case of multi-instance modeling. So this is our topological modeling. So we have a molecular graph. We encode each atom by a set of features, for example, charge, number of explicit hydrogens, atomic number, and so on, aromaticity, hybridization state, whatever. Then we pass these features through convolutional layers and get some embeddings for every atom. And then these embeddings by these authors were used to to calculate the prediction of micro pKa for every atom. And afterwards, those predictions were aggregated by this equation to predict macro pKa. And what is important here is that micro pKa is not easy to measure experimentally. Usually we observe macro pKa and we model these properties. So this property of a whole molecule, but only separate atoms contribute to acidity of those molecules. And this approach helps to not only predict the final pKa of a whole molecule, but it also helps to identify which atom contributes the most. So it can return prediction for every particular atom in this way. And researchers tested the approach on several data sets. For example, Han data set, it's a manually curated set of compounds where human experts annotated atoms which should be responsible for acidity, which contributes the most. And as you can see, correspondence is very high. So almost in 100% of cases, the model can identify proper acidic center. Here is an example of those properly identified centers of acidity. And they also analyzed in which cases it didn't happen. So in which cases the prediction somehow contradict to the human expert. And they discovered that in almost all cases, it was attributed to those hydroxamic acids, where humans annotate as those green circles acidic centers, and model predict that nitrogen would be more acidic. And this is quite easy to explain because for such kind of compounds, in reality, the acidity of those oxygen and nitrogen very close. There are quite a lot of evidences in literature that it is very difficult to decide which proton will dissociate. In some cases, yeah, they missed, but it's difficult to decide without experiment which atom is more acidic. So if you can fix this data set. So it's really difficult for humans to decide. But nevertheless, this agreement is very high. So for almost all molecules, they identify correct atoms. Peptides, they can also be an instance. These are already examples from bioinformatics. Here is a study. I just briefly discuss a general idea without much details and numbers. This was a case of major histocompatibility complexes of class 2 proteins. It means these are part of our immune system. When phagocytes take some alien protein, then these protein are cutted by lysosome inside a cell, and those short sequences are bound to those molecules, peptides, class 2, MHC class 2 peptides, proteins. And this peptide binds this short sequence and go to the membrane and put this sequence outside of a cell, and then specific T cells of the immune system recognize this as something dangerous or not dangerous and create immune response. And what is important in these cases, this scenario quite important for even now during this COVID period, because it is useful and important to know which sequences can cause immune response. And this, if we know in advance which sequence can cause an immune response, when we design vaccines, we can consider this, and we can try to avoid using these subsequences to not trigger immune response if we don't know it, if you don't need it. And the issue here is that those sequences which are got in the cell, they are usually from 11 till 30 amino acids. But only a short subsequence of this whole peptide is important for binding, because those proteins, they have a groove which can accommodate 9 amino acids. And we can use the whole sequence for modeling, for prediction, but it is more profitable and beneficial to represent this sequence with subsequences using a sliding window, and use all these subsequences as a representation of our whole sequence. And these are instances. And then build a multi-instance model, predict a property, and as an additional option, we can get some important features, key instances from this model. This is an example from bioinformatics, and another example from bioinformatics. For example, we can think about instances. This can be proteins, isoforms, domains of proteins. For example, in this case, researchers used isoforms to model gene-gene interactions. So if we have several peptides which they can work all together, for example, if we have 2 genes, and if one of them are knocked out, we will still have big effect. We will observe if the second one is working, but if we will knock out both of them, we will not observe the same phenotypic effect. There are some other cases which occur. But when we consider those gene-gene interactions, we may consider classical only single isoform. But due to the splicing or other effects, the same gene can produce different peptides, different isoforms. And if we will consider them, so in this case, when we represent our training objects, we can have, for example, for gene 1, 3 isoforms, for gene 2, 2 isoforms, and out of 6 possible pairwise interactions, 2 of them are really occur. This is a positive case. In negative case, all isoforms do not interact with any other isoform of a second gene. And this gives us more complete picture. So this case is a traditional modeling when we have just one instance on each site. And these are multi-instance model, and we try to separate them based on these pairs which are relevant. Because if we use just the canonical isoforms or the longest isoforms, we can miss this information because those canonical isoforms may not interact in reality. And this adds noise to our model. So in this case, we can improve this prediction. So just as to summarize all what I said, that multi-instance demonstrate really good accuracy, and it clearly outperforms 3D models. It even outperforms 2D models, and this can be a good choice if you try to build your machine learning models using classical 2D descriptors. You got bad result, and okay, you can consider multi-instance learning as a choice, additional choice to improve your predictions, as I showed you. Ability to identify those key instances is also very attractive, and it is still unexplored. But I hope that these things will change soon. Actually, I'm looking for PhD student who will continue this work, because we did the previous part, and now he defended his PhD thesis. So if you know somebody who will be interested in machine learning models, working with multi-instance problems, you can invite him to contact me, and we will discuss. So that's interesting, really intriguing question, whether we can identify those bioactive conformers without knowledge of receptor. So preliminary results show that yes, we can, but we should to understand to which extent. And there is still lack of benchmarking data sets. So this also should be created to benchmark more properly these issues. And the last but not least, that almost everything can be considered as instances. So when you build QSR models, what you do and what you will see today, you get in classical case, in classical scenario, you get a single representation of your molecule. So you should generate particular tautomer. You should decide which stereoisomer to use or discard the information about stereochemistry, for example. Again, which protonation state to use, that also may impact somehow your model. And it is not so easy to decide which tautomer is relevant, which protonation state is correct. And in multi-instance learning problems, it's solved naturally. So you can get all together, generate all possible tautomers, protonation states, and get in one bag and use them for modeling. So this is also an option. I don't know how much improvement will be. In our preliminary experiments, we didn't observe much improvement because normally there are not so many tautomers, not so many molecules with different tautomers in our data sets. Or another issue, the descriptors which we use cannot capture those tautomers properly. That's also possible. But nevertheless, that's possible. So atoms, sequences, subsequences, everything can be considered as instances, and multi-instance solutions can be applied. So thank you for your attention. That's all from my side. I'm sorry for a little delay, so I wanted to show you everything. So questions from the audience? Or you are overloaded with so much information after yesterday dinner? It's very difficult, very difficult. Do we have some questions from online?
Yeah, here is one question. Can this modeling be done for protein metal ion interaction?
Protein metal ion. What would be the instance in this case?
Well, one possibility that came to my mind is that you have some binding space for the ion, and you want to find out which ion will bind there best. For instance, by zinc or copper.
But in this case, it happens that ions are back, and particular ions are in instance. That's quite strange, because all bags will be the same in this case, because you have the same set of ions in this case. It may be, I just hypothesize, so that's quite unclear question. So if you will be able to specify more detailed, I will answer it. But I just hypothesize, if you have, so for example, multiple binding sites for your ion, yes, in this case, you can use these binding sites as separate instances and build a model. And model will predict your affinity of your metal ion and can deconvolute which particular binding site of each ion. This could be a way how to apply multi-instance logic for such tasks. So there is no details, no more. Okay, so thank you. We will make 20 minutes break and then continue with de novo design. So we can start the next lecture dedicated to de novo design. This is maybe the major topic on which my group works currently. So we develop different tools, and I will introduce you some basic tools during today's tutorial, and I will discuss in more details these approaches. So de novo design. How many compounds were already synthesized and how many compounds can be synthesized? These are interesting questions. Here I just selected some libraries. Some libraries. These are commercial libraries, KeyFinder, Reaxys, which had more than 100 million compounds in their databases. Not all of these compounds are organic compounds. They can be inorganic as well, but majority of them are organic compounds. There are also PubChem database, which also has more than 100 million compounds registered. And with some annotated biological activity, we had Zinc database, which had more than 1 billion commercially available compounds collected from different vendors. And when we think about these numbers, they look pretty large, pretty huge. But in reality, this is almost nothing in the sense of a whole chemical space. For example, virtually enumerated library with up to 17 atoms contains 166 billion compounds. Of course, it is not the exhaustive enumeration. They applied some restrictions because exhaustive enumeration would result in much more number of compounds. And this number is also quite large, so it's 2 orders of magnitude larger than this one, but it is almost not so large. Here is a collection of virtual and commercially available and actual libraries of compounds. And the number of approved drugs is less than 10,000. There are some public data sets, this GDB17, some commercial data sets, and these are proprietary virtually enumerated libraries, which are quite frequently started to be used in industry. And the largest library contains 10 in power 20 molecules. So these compounds can be generated on the fly. So these compounds are not stored on some disk because it is not possible. There is not enough space on the Earth to store all this data. So they are generated on the fly, and they estimate that the size of a library can be 10 in power 20. But even this number is not the final one. So this is a really very, very, very tiny portion of a whole chemical space. As we estimated, drug-like chemical space contains 10 in power 36 compounds. And those are just small drops in this ocean of possibilities. So this is a number of compounds which can be drug-like according to the Lipinski rule with a molecular weight below 500. And this creates a big challenge for us as researchers to find some useful compounds in this chemical space. And the question is how we explore this large chemical space with the help of available databases or virtually enumerated or in some other way. And in this case, we have two approaches. I mean computational approaches to explore chemical space. One of them are virtual screening. When we take a database of molecules, apply some model, and select top-ranked compounds for actual screening, experimental screening. And this process can be applied to billions of compounds at most, because it is not computationally efficient. Even very fast calculation in multiple servers, it is not so easy to produce results for multi-billion sets of compounds. And since it can screen only a very small portion of a chemical space, it can be more useful to explore the whole chemical space in a more advanced and reliable manner to discover new chemical entities. Because if you screen the same database each time, you have the constant chemotypes, and you cannot discover something completely new. And this may issue with patentability of your compounds and so on. And if you will try to explore somehow adaptively across the whole chemical space, it can be beneficial for us. And de novo design methods were developed explicitly for this reason. So we can, for example, iteratively going through this space from one compound to another in searching some better one. We may not find a global minimum, of course, but we can try to explore much larger chemical space. We can discover new chemical entities with these approaches. And these approaches can be applied to explore even such a large space like 10 in the power of 36 opportunities. And we will focus this presentation explicitly on this topic. Here is a classical workflow of de novo design approaches. They use and consist of three major steps. The first one is a structure generation. So how we create computationally molecules. Because for humans, it's quite easy to draw a molecule, but for computer, we have to explain how to create new structures, which should be reasonable, chemically reasonable, and so on. Then the second part is scoring or prediction of compound properties. How we which objective function we use to guide our search, what we want to optimize. It can be different types of models. And the third part is a selection. So on each iteration, we select some better candidates, put them on the next iteration, generate new structures based on these structures to explore some local chemical space around them. Then again, predict the property of these compounds, select once more better candidates, and this can be repeated in multiple cycles while we explore and travel across this chemical space until we find compounds with the desired property. Regarding structure generation, this is the most important issue for de novo design method for many years. And multiple methods were developed to generate structures. And they can be split on two, in my opinion, large groups. One of them which do not use machine learning. So they consist of atom-based, fragment-based, and reaction-based approaches. And separate group which use modern deep learning techniques. So we will discuss them in more details. So atom-based approaches, from its name, it's clear that when we generate new structure, we use very small changes. So we can add atom, add bond, remove, so on. So we applied very small perturbation to our molecule and generate a new one. One of such generators were developed in Prague in Daniel Swozil group in Veshachate. And here you can see some examples of those basic operations which can be applied to molecule to generate a new one. So so they are very simple. So remove, mutate atom. So very basic scheme. They applied this approach usually in settings. They have two compounds and they generate a route from one compound to another one in sense of chemical structures. So they mutate from one structure to another to sample chemical space between 2 points. And these compounds are used to were used to predict properties and select better candidates. What are good stuff of this type of approaches that they can really exhaustively explore your chemical space, because you can visit every, I believe you can generate every possible molecule, because it's based on very, very low primitives, just one atom. So you can put one atom, get new molecule, and so on. So it's very good in this sense. But the another side of this advantage is that generation is very slow, because you can generate a lot of possibilities and you have a combinatorial explosion if you want to search in a more wide manner in a chemical space, because from each molecule you can generate multiple new structures, and you make very small steps in chemical space by changing just one atom or one bond. And to go somewhere further, you need a lot of such small steps. And this is computationally not very efficient. But these approaches exist, and they result in a very good novelty, because you can generate any scaffold, any cyclic system. They can generate very diverse sets. Chemical validity, yeah, it is not always possible, but they have some heuristic to reject invalid molecules before. But some invalid molecules can be generated by this approach and filtered afterwards. And the biggest issue is the synthetic feasibility. So molecules generated by this approach are not frequently, do not have frequently good synthetic accessibility. And this is some trade-off between novelty and synthetic feasibility. That's always happened in de novo methods. So if you generate two novel molecules, maybe nobody will know how to synthesize it. If you generate something known, okay, everybody wants to know how to synthesize them, but there is no novel. So there is always a trade-off, and it's quite difficult to find a balance. So I compared these atom-based approaches with ab initio approaches from quantum chemistry. So it can generate and explore everything, but with a high cost. Another group of approaches are reaction-based. So from its name, it's clear that chemical reactions are used to create new structures. Here are one of the first examples of this approach, developed in a group of Professor Schneider from ETH in Zurich. They created a library of reactants and a list of chemical rules which can be applied to these reactants to generate new compounds. And they used the same iterative procedure, and they grow molecules by applying coupling reactions, selecting on each iteration some good candidates and put them on another one. They made this to simplify the search. They made this consisting of two steps. On first step, they select which reaction to apply. So they apply individual reaction with one reactant to get one product, then make prediction. Based on this prediction, they choose which product and reaction won, and then they exhaustively enumerate all possible products using this particular transformation with all other reactants. And this procedure repeated iteratively to discover something new and useful. And here is an example of what they did. So they tried to identify gamma secretase modulators. And here you can see how they achieved this one. So this molecule was a reference one, and they tried to find the molecule with the highest similarity to this one using the procedure. Finally, they found a compound which was active. Unfortunately, it was inverse modulator, but that is not very important. More important that they were achieved. So to perform this reaction, the procedure was very fast, And using the simple similarity cannot guarantee that you will find particular functional response. But nevertheless, they prove that this compound can bind to gamma secretase to modulate its response. So it's one of the first examples. Some later examples from the same group. Yes, from the same group, where they tried to identify new retinoid receptor modulators. They took some natural products, some new one, and then use them as a template for similarity search using the DOCS approach with reaction-based de novo generators. They finally could achieve and generate some useful molecules, and they were able again to make those molecules according to the predicted reaction routes. So that's really good. And they found that some of these compounds were even more active than the starting templates. So this is again another one example how it can be useful. So de novo design is not just a theory, it can contribute to your practical work as well. So what are advantages of this approach? So with reactions, you can cover less chemical space, of course, in comparison with atom-based approaches, because you cannot visit all possible compounds. Not every compound can be synthesized according to the limited list of reactants and reaction rules which are used. Structure, this also somehow decreases the novelty and diversity of generated hits, but at the same time, structures which are generated are always chemically valid and they're synthetically feasible with very high percent successes. And they do not have combinatorial explosion issue because there is a limited number of opportunities to generate new molecules. Of course, they have, but not that much as atom-based approaches. Fragment-based approaches. They are somewhere in between of atom-based and reaction-based approaches. They can be used in different modes. For example, they can grow your fragment to attach new one. Actually, with reactions, what I can say additionally, that I didn't see paper where they applied non-coupling reactions. So they always use coupling reactions to grow a molecule. And this is similar to the grow procedure with fragment base. So we can attach fragment to an available molecule to grow them up, or we can replace fragment on another one. In this case, we apply mutation operation. Or we can link together two fragments to get a new molecule in fragment base. Or we can remove some fragment from a molecule. In such a way, we reduce our hit compound. So it allows, fragment-based allows more moves than reaction-based. But they do not, they perform it on a little bit higher levels than the atom-based approaches. So we have some set of fragments. Here are some historical examples, which are just for inspiration, for better understanding how this works. Here is an example. If we have crystal structure of two ligands in a protein pocket, and those two ligands share the common or similar scaffold, what we can do, we can cut them and we can switch them off. So we can each fragment for another one. And in this way, we can generate new molecules. This was done for a really resolved structure with clearly known binding mode. And what they demonstrated that here is four ligands which were known as HIV protease inhibitors. And they applied this breed approach. And so they replace fragments from different molecules, and they found compound which is even more active than all training set examples. So just recombining fragments gives you better molecule. Of course, in this case, you need explicit knowledge about the poses to be sure that they properly superpose and this fragment can really replace each other. But it is quite interesting and fruitful approach. Another approach which I personally like, however, I didn't find some practical use cases. You don't need to understand all this complex procedure. I just demonstrate that it is relatively complex, iterative as well. The idea behind that the researchers put inside a protein pocket small fragments and then run molecular dynamics simulation for rigid protein and flexible residues, which are mixed with water molecules. And during this simulation, they enable opportunity to create new bonds between fragments, between atoms. But not all bonds can be created. So to generate some artificial molecules, they forbid to create particular types of bonds. But this like the most close, maybe like a bowling soup. So inside this fragment, and they somehow randomly combine and decoupled and create something reasonable. They applied this for HIV protease inhibitors as well. So at the beginning, they start from this methyl formamide. So they put these molecules inside, add water, started to their simulations, and they could recreate some backbone of a known inhibitor, because known inhibitor is also short peptide. So they were able to recreate this backbone somehow at some to some extent. Then they add fragments, other fragments, and continue the simulation. And these fragments create side chains of this backbone, And they show that they quite nicely reproduce the structure of a reference ligand. So it's interesting, but it is very computational inefficient because you need this MD simulation. But in this case, you can see some dynamics. But unfortunately, to be effective, they make protein rigid. So that's also a limitation of this approach. But maybe in future, when computers will become really powerful, we will be able to simulate something similar. More reasonable way how we can link fragments, how we can create new molecules, Hook approach. Researchers existing molecules and they calculate probability of frequency occurring when two fragments are linked together. So these are probability in how many cases phenyl linked to another phenyl, for example, oxygen, chlorine, or furane. And this is for every fragment. So chlorine atom cannot be linked to oxygen or another chlorine. So there are zero probabilities, and they create so-called Markov chain. And then when they generate, they just randomly sample starting fragment, then select with the proportional to the probability the next fragment from these three, for example, furane with the probability 0.1, and then attach this fragment together. And this procedure can be repeated multiple times to grow your molecule. That's quite smart, but what is the disadvantage? These linkages are created in random positions, and generated molecules are not always synthetically feasible, for sure, because some linkage can result in non-feasible combination of fragments. More sophisticated approach was to annotate every fragment with attachment point. So they cut existing molecules on fragments and annotate each attachment point with the type of atom to which this atom is attached. And when they linked together those fragments, consider this attachment point. So these are a little bit more strict. So they limit to which position it can be attached, but it is still not enough, because sometimes substituents can be introduced in ortho position or meta position, and this can be encoded in this way. We suggested and implemented the software, which is freely available, also for fragment-based generation, which is quite similar to the previous idea, but in this case, we annotate every fragment. So we take existing molecules, exhaustively fragment them, and we annotate every fragment with attachment points and with chemical context of a particular radius. So not a single atom, but several atoms which are close to this attachment point, with radius 3, with up to 3 bonds away from this attachment point. After that, we get this for every fragment, for every molecule. And after that, we create a database of these fragments and environments, chemical context. And this means that if fragments occur in the same environment, they're interchangeable. So you can be more or less sure that if you exchange these fragments, you will get a synthetically feasible compound. And this procedure is very fast for designing new compounds. For example, you have a new one and you want to replace this fragment. You again cut this fragment, calculate environment of a given radius for this fragment, and then search a database. And if you find an environment, this particular environment in database, you can apply all these fragment replacement for your molecules and generate new ones. And with high chance, those compounds would be feasible and always chemically valid. So, and if you choose a large radius, you can take into account ortho, meta, para position, and so on, if you need this. So what are features of fragment-based approaches? So they are less exhaustive than atom-based, by more exhaustive than reaction-based, because more number of moves are allowed to do. The structural novelty and diversity is also a little bit larger, in my opinion, than in reaction-based approaches, but of course, they're far behind atom-based approaches. Chemical validity of structures, I think, happens only with introduction of this CREM, chemically reasonable mutation framework, developed by us, because before that, they cannot guarantee with high confidence that molecule would be chemically feasible, because they do not consider this chemical context, and just random linking fragments do not result in this. And synthetic feasibility, so it is somehow moderate computational efficiency, but it can be tuned, so you can tune these approaches by the size of a fragment, how many replacements you want to do. So they're highly flexible in this way, and you can apply this procedure even on your laptops, and you will see during today's tutorial how to do this. I particularly wanted to compare reaction-based and fragment-based, just to summarize all I said previously. So reaction-based approaches, they need the set of reactions and building blocks. So this can be quite feasible building blocks taken from different commercial vendors. Reaction rules you have to create by yourself or from literature, and which reactions to consider, it's up. For fragment-based, you just need a database of fragments, which are usually obtained from existing molecules. And for reaction-based, once more, they give synthetically feasible with high confidence. In fragment-based, we cannot say that it will be very high confidence, but with certain confidence, we can do this. In what I wanted to illustrate, that, for example, those arrows, orange arrows, demonstrate possible chemical transformations, how molecules can be created. And these blue arrows demonstrate moves which can be applied with fragment-based approaches. And this just much more possibilities how to move. And not every move is possible for reaction-based. For example, if you have a phenol, you cannot get a toluene in one-step reaction. and so on. Some molecules cannot be achieved easily with synthetic routes or will require multiple steps, because usually these run for 2-3 steps reaction, not more. So fragment-based allow you to more exhaustively explore chemical space in a more flexible way. And if you get a chemically reasonable compounds, you can be a winner. Here is the overall summary. We can skip it, and we can go to the modern models, how we can generate molecules using deep learning methods. Here is a recurrent neural network, and it takes in input just a smile. Smiles is a string which encodes molecular graph. So it's just the set of atoms, ring closures, and so on. And the model trained to reproduce this smile. So it takes some initial symbol, and then it predicts next symbol in a string. It predicts this symbol, it combines to the string, and then make a prediction of a next symbol. And in such a way, they iteratively grow your smile string, and this smile string can be a valid chemical structure. So this is just a text. And this idea came from the text processing. So it's not originally from chemoinformatics field. This is quite easy, fast, smart. But the issue here is how valid are those strings? Can we always create a molecule, a valid molecule from these strings? And how they can be used in reality. So in one case, for example, a model can be trained, for example, on a whole Campbell, and then you just ask them, okay, generate me some random molecules. And it can generate you a lot of molecules without any idea about your objective function, what you want to optimize. Or if you train this molecule on a whole Campbell, then you can additionally train this model on a small subset of ligands which are interested for you because they have particular scaffolds or properties. And if you will repeat this procedure several times, this will create a bias. And the model will start to generate molecules which will be more similar to those ones. This is a way how we can tune these models to guide them to generate something useful for us. Here is just examples of how compounds look like, which are generated by this approach without any supervision, without any biasing. And researchers of this paper found that almost among 1 million compounds, almost all were chemically valid. Some of them were, of course, identical to available in the training set data. So this model will reproduce known compounds with some percentage. That's also possible. And of course, there will be some duplicates. And I would say these results are really good because when this approach started to appear in literature, I could find a lot of papers with a very wide range of values. In some papers, they claim that, okay, we train a model which can produce just 5% of valid structures. So the range of values was very large, and this one really, really great result. Here is just a comparison how those generated molecules map to the Campbell one. So they're pretty similar, and they occupy almost the same chemical space. So what to say here? I will just point out that, again, if chemical validity somehow can be solved, synthetic feasibility of generated compounds are unknown. And it is still the issue for these methods as well, because they know nothing about chemical feasibility of those compounds. Some other issues that compounds can be represented by different smiles. It can add noise to these models, but somehow this was solved in recent developments. So this technique was probably, I can say that it is one of the best approaches today from deep learning methods to generate new molecules. There is a reinvent a development which used all the same idea behind, and it becomes quite popular. Okay, so we talked about generators. Now, what we can use as a scoring or objective function, what we want to optimize and how to use it. So we can use any kind of objective function, and this gives us great flexibility of this de novo approach. So we can optimize simple physicochemical properties. We can use similarity measures if you want to generate analogs of particular compounds, for example. We can use QSR modeling, pharmacophore modeling, docking, whatever. So any kind of models can be applied. Maybe the only issue may occur is how rough or smooth your search space, because optimization methods, they like more those smooth space, search surface without some sharp changes, deep grooves, and so on. So it's because your molecule can stuck in some local minima and you will not be able to travel further. So it depends on your search algorithm. So they prefer some smooth function. But again, if you will use quite advanced algorithms, search algorithms, this will not be a problem. And again, you can combine with any kind of search algorithm, this de novo approaches. So you can use greedy search, stochastic searches, Monte Carlo, or evolutionary searches, whatever. So they can allow you to skip this local minima, go further, and so on. But this is not the main topic of today's lecture. So here I just briefly remind you about the general workflow. So we have 3 major steps, which are iteratively running and generate better compounds. And yeah, of course, we can combine objective function together. So we can optimize multiple properties simultaneously as well for de novo. Yeah, it is challenging that if you combine multiple properties, and if every property, for example, can be predicted with 90% of accuracy, and if you combine 10 of them, the overall probability to find compound which satisfy to all these 10 property will be relatively low, even with very accurate models. So you should consider how many properties you want to optimize simultaneously, but 2, 3 is okay. The next part, what Mariia started to tell you about inverse QSR. Here is the traditional way how we create models. So we have a structure, we generate some descriptors, and then we get some model which can predict our properties. And this model is just a very complex function, nothing else, just a very complex function. And it can take different combination of descriptors and gives corresponding response. And if this is a function, you can optimize this function and found extrema, minima or maxima, it depends on your goal. And after that, when you find extrema, desired extrema, you get some set of descriptors which describe this local point. And then we can think to consider how to deconvolute this set of descriptors into the structure. And this would be the most direct way how we can use machine learning to generate desired compounds with desired property. So directly from models suggest what to synthesize and test. The issue here is that how to make this last step. That's not trivial. Here are quite old approaches, how researchers try to combat this issue. So they use specific descriptors topological descriptors and set of linear equations with restrictions to find the QSR model, optimize it, and find the good combination of descriptors, which can be then iteratively try to reconstruct from those fragments the target molecule. It is not very efficient. It is limited to particular compound, sometimes missed or swept some fragments because they will have almost the same set of descriptors or the same set of descriptors. A little bit later, strategies which were suggested to use for modeling, for example, descriptors which are extensive descriptors, which are always increase its value with increasing of a structure. So you attach atom or fragment to your molecule, and the value of those descriptors are increased. And in this case, if you define some desired space in your feature space, and you can start to iteratively generate molecules using some generator, and this path will go in one direction. So it will always go forward due to this property of those descriptors. And when your molecule reach this region, you can say that, okay, this molecule corresponds to the desired region, and it probably will be active. It is also not very efficient, and it requires, again, some structural generator. So it's not fully independent. More interesting approaches were to use autoencoders. So these are modern neural networks, which takes as input an object, pass through multiple layers to get some dense representation, some compressed embedding, and then another set of layers try to decompress this compressed representation to get identical or similar object. So this can be used for images, for everything, and for molecules as well. Why not? So we can pass smiles and compress it and get a smiles as output, for example. Why not? And this can be used already for direct inverse QSAR problem. What researchers did? So they use smiles as input, encode them in some latent embedding. They are just two-dimensional, but of course they are more dimensional. And they could decode some structures from this latent space. And this latent space, this can be considered as ordinary descriptors. And we can use, for example, random forest or neural network, whatever model, to build a model to find the correlation between these descriptors with our target property. So here's a property, and since this model is just a complex function, as I told you, we can optimize it, find some extrema point, and we got the coordinates in this latent space of this point, and we can sample molecules from this local environment of this point. We can with this decoder. And in this way, we can generate a lot of possible candidates, which would satisfy our QSR model. Here is an example how they generate molecules starting from one and drug likeness and synthetic accessibility score. They got through multiple molecules. They correspond to this trajectory. So how they correspond to this optimization trajectory, these molecules. So they improved their properties. Everything perfect with one exception. Molecules which were generated in this way shouldn't be theoretically feasible. For example, in this paper, they published a pretty interesting motif. I tried to search literature, and even in theory, it cannot exist. So even in theory, such ring system cannot exist. Maybe in some very unusual conditions, maybe, but there are no clue. So this is the biggest issue for today for all generators and de novo methods that, okay, we now can generate molecules. They can be chemically valid. But what about the synthetic feasibility of those compounds? There are several cases how we can introduce synthetic feasibility to our de novo design process. Here is a conventional virtual screening. So we have a database. We somehow filter them by synthetic feasibility and then make prediction. Okay, but virtual screening cannot allow us to screen the whole chemical space or explore it efficiently, so we don't use it. Standard generation, they do not use any bias to synthetic feasibility by default. And we can introduce in different ways. For example, we can post-filter generate molecules according to some synthetic rules, for example. This is not a bad choice, but in some cases it can be really bad because we can remove all compounds from our hit list because all of them will not be synthetically feasible. So this way may be not the best choice to post-filter generate compounds. More clever ideas that we can bias a training set which is used to create our generator. We can select the only synthetically feasible compound to train our generator and use this already pre-trained generator. And we can hope that it will generate synthetically feasible molecules. That's one way. Another way, we can introduce synthetic feasibility rules or some heuristic in our evaluator. So we simultaneously optimize target property and synthetic feasibility in this case. So this becomes multi-objective optimization problem. Another way, we can introduce synthetic knowledge in our generator explicitly. This is the case, for example, of reaction-based de novo design methods, when we explicitly restrict generator to make only certain moves based on reaction rules. And the question is how to assess synthetic feasibility, because we cannot ask chemists to look through the millions of molecules, to rank them somehow, to make a conclusion. So we need some computational approaches how to assess this quite fast. And there are quite a lot of them. Some of them are based, for example, on retrosynthesis. So we can reproduce retrosynthetic paths to some building blocks of our molecules with Asin Finder, for example. It is pretty fast. It works about 2 minutes per compound to predict the pathway. But if you want to screen millions of molecules, it's not that fast. So that's why those researchers decided to create some simpler models. They predict the retrosynthetic paths for available molecules, and those which were can recreate the synthetic pathway, they were labeled as positive, others as negative, and they train an orderly classifier to classify positive and negative molecules, for which the generator can create can predict retrosynthetic pathways. And another approach which was developed in Prague, and again Daniel Swozil group, is SIBA. So they also train classifier, Bayesian classifier, to discriminate between synthetically feasible compounds, which they took from existing molecules, and synthetically non-feasible compounds, which they generate artificially with their atom-based generator. So they have generator which specifically generate synthetically not feasible molecules. And they build a classifier which can discriminate these two sets of compounds. But many of those scores, they quite well correspond to the score, synthetic accessibility score suggested by Peter Ertl in 2009. The idea behind this score is very simple. He analyzed the frequency of different fragments in PubChem database and decided that fragments which occur frequently are more synthetically feasible, less frequently occurred fragments less synthetically feasible. He built just a simple linear regression with some weighted coefficients according to the occurrence of different fragments. They add some additional bias to account for stereochemistry, some linkage, and so on. And these scores are quite popular and widely used, and they well correlate with the previously mentioned scores. They are from 1 to 10. 1 means synthetically feasible compounds, 10 means synthetically non-feasible. Here is a distribution for Campbell, these values of synthetic accessibility scores, and here are just examples how they look like and what corresponding score of these compounds. I took just random ones from this distribution, just to illustrate the idea. So how we can tweak synthetic feasibility with different tools. For example, with CREM, with fragment-based approach, we have several opportunities to change synthetic feasibility of our molecules. We can use the strategy, this one, so we can bias training set. So we can use for fragmentation not whole Campbell, but molecules with predicted very highly synthetically accessible. And from this small number of molecules, we can create fragments and use them for generation of compounds. Or we can change the context radius, as I described to you, from 1 to 5, for example. And this will also make restriction similar to reaction-based approaches. So we explicitly restrict which moves it can make. So if we make very large context, we will make very conservative replacements. So it will consider up to 5 atoms away from the attachment point. And this number of replacements will be very low, but in this case, we can expect that we improve the synthetic accessibility of generated molecule. We performed an analysis of this approach and these setups on guacamole benchmarks. And compared to some literature data. And what we observed that, as expected, if we increase the context radius, we see that guacamole score, it is on the x-axis, it becomes lower. So the top score is 10, so they reach up to 9. But if we increase the context radius, they will become lower for all databases. And here is the synthetic accessibility score. So the lower, the better. So the sweet point is somewhere here, where we have high score according to the guacamole benchmark and low score according to the SA scoring. But no methods achieve this point, but everybody tries to do this. And we observe the same expectation from biasing the training set. So if we took more restricted fragment database, we get, of course, a little bit worse guacamole scores, but much better scores in synthetic accessibility. And these approaches from CREM, from fragment-based, they're competitive to some modern approaches based on LSTM models or genetic algorithms based on smiles or graphs. And even if they're explicitly biased by synthetic accessibility score, those pink points. So even in this case, CREM can outperform them, or at least perform comparably well, according to this benchmark. And the last example, which is quite interesting, it was published recently in Nature. It comes from a ChemSpace company, which is somehow daughter of Yenamin. It's a Ukrainian company. It's the greatest provider of chemical samples today. They create a pipeline, reaction-based pipeline to generate compounds de novo and make this iteratively. So they annotate the building blocks, reaction rules. Then they generate some starting point. So they kept those possible attachment points with small but reasonable counterpart according to the reaction rule. They dock them into the binding site. Then they decide which points can be grown, and they apply a reaction to grow these molecules, to enumerate next step of next generation of compounds, dock them again, and repeat this cycle so many times as how many reaction steps they want. They require this docking was made for millions of compounds to make this procedure efficiently explore the chemical space. And this is the way how they explore their virtually enumerated enamine real space, which currently contain about 30 billion compounds. So these are virtual library of compounds which can be synthesized with 80% of success chances according to enamine information. So they repeated this several times, and they got these primary hits. They were not very highly active, so cannabinoid receptor 1 and 2. They tried to design selective one, but on the first step, they just identify some good starting points. Some of these compounds have a submicromolar activity, so it's a good starting point already. They further optimized those molecules. They took one of them as a starting and then tried to change different substituents according to their reaction rules. They enumerated, again, dock them, evaluate, and then finally test. And they found very, very nice compounds with high, where it is, yeah, this one. So with very high selectivity and very high affinity, here is nanomole. So it's a sub-nanomolar activity compound with high selectivity. So this can be achieved in a quite short timeline because they can reproduce their own reaction rules quite well. And this is a great example how we can explore really large chemical space. And I believe that they will go beyond this 30 billion and they will go to the, I don't know which numbers, but this is just a question of time. So at the end, what I would say, the de novo methods are really useful. They can be applied. I will show you how you can do this by yourself, just to trust to my words. Currently, we have multiple approaches which can generate structures. But the biggest issue, we should do this in a chemically reasonable way. And synthetic accessibility still remains the main issue of all these generators. That's why the current trend is to search for reaction-based approaches, mainly, not to other one. But I believe that this CREM approach is quite competitive. So we had some preliminary results. So that's all from my side. Thank you for your attention. Questions? So I'm in time. That's unexpected. So do you have some questions? Did you understand how this works, these de novo methods? So this is really hot topic in cheminformatics. And there are a lot of groups who works, but mainly they focus on those generators. But I think the generators is, if you cannot create generator with some synthetic knowledge inside, maybe it's not so reasonable to develop it because there are a lot of competitors on the market already. So it will be even probably difficult to publish such papers. But nevertheless, this is a really hot topic for research. And we are working hard to incorporate this structure-based generator to different models. And I will show you several examples during the tutorial. I prepared some slides, introduction slides. So do we have some questions from the online? No? Okay, so we can go for a lunch for 1 hour, and we will meet at 1 o'clock. Не знаю.
Да, смотреть. Я не знаю, когда у вас будет время.
Смотреть? В смысле, какую?
Моя